let's look on the black box here. So we all will run some ambitious jobs, much bigger than this 9 atom or 60 atoms examples. So what if I'm not happy with 30 minutes and I want to run for 24 hours? And what if I'm not happy with 64 CPU processors? If I want like 1,000, what should I change in this submission job script?
So we can simply put a regular in the place of debug.
Okay, and what then?
And it's going to it's like the regular is for our heavy job or the more time-taking job.
So you're telling that if you change debug to regular, you can increase time to bigger numbers. So instead of 30 minutes, you can put 24 hours, right?
We can simply put change the time as well, and it's like it's not putting into the schedule or it's going into the regular job.
Okay, good. And if like this example tells to run job on one node, one box, and use 64 CPUs.
Yes.
What if I'm running a big model and I need more than 64 CPUs? What should I do?
So I guess we can change the CPUs here.
Will it give an increase in the performance?
Yes, obviously for a longer job.
Wait, no. When it's simultaneous, like each box, each node has 64 CPUs. So if you keep number of nodes 1 and request like 128, it will just give double job for each CPU, but it will slow down rather than speed up. So if you increase this number twice, you need to increase this number twice as well.
Yes, sure.
Okay. Any additional questions to Umar? I do have a question which just for everyone to think about. If you have answer, please speak. If you don't, it's fine because it is a longer discussion. So for what is the command? So it's question not literally to you, to everyone. What is the command module? So module load, module show, module swap on NERSC. Later on, when doing absorption spectra, we are swapping the modules. So do you see any, can you comment, would you like to comment on it, or you better let others speak about it?
I don't know about that part.
Okay, that's fine, but let's think about it and we can discuss it tomorrow in the lab.
Sure.
Okay, more questions 1, more questions 2, more questions 3. If there are no more questions, let's thank Umar once again. Umar, you're welcome to stop sharing. And I believe next presenter is Adam, right?
Yeah, can you hear me?
Yes, I can hear and see you. Would you like to share your slides?
Yeah.
Okay.
Okay, here we go.
Floor is yours.
All right, so I'm just going to be talking briefly about modeling electronic excitations in VASP. So we have a few like prerequisites, something that we need to do before we can do this. So we need to, make a new directory and select the desired system. We need to import our postcar, potcar, and kpoints files from a, just a previous computation. It can be, it helps to have a previous computation. And specifically, we want to find the number of electrons so that we can get our HOMO for the ground state. So that would be 16 in this case with 32 electrons. And also we want to have our states file just kind of with this pasted in. And we can use this command to kind of help us, determine the number of electrons from an outcar from a previous computation. So we're going to be looking at, what this excited state configuration would actually look like, the difference. So of course, these electrons from 16 jump to 17 during an excitation. They just jump up in orbital, and also these energies, you can see they change. The gap changes significantly as well between these two states, as they would be expected to. To do an excitation, to model it, we want to manually specify the orbital occupancy. So you want to say, so here are the orbitals that are occupied, here are the orbitals that are unoccupied. So we're going to be using this in-car Furby. And what that does is it adds this tag that allows us to kind of just manually input which orbitals are occupied and which orbitals are not. So 0 is unoccupied, 1 is occupied. And we can say for the first A orbitals, they are occupied. Then there's an empty orbital, and then there's a full orbital, and then the rest of them are empty with B. So that's essentially just what the tag does. And when you run the optimization, you can get the density of states plots for the respective excited states, which are obviously going to be different from the ground state. So that's pretty much it.
Okay, please join me thanking Adam. Adam, please do not remove your slides yet. So are there any questions about this skill in the chat line or by verbal? I do not see one. So let me ask, I scratched a couple of questions. So you did show an excitation from HOMO to LUMO. Does your method allow to create higher excitation, to excite different pairs of orbitals?
I believe so, yeah. Like just through manual specification, you can you could go higher, yeah.
Okay. If one uses this Ferrier constraint and performs geometry optimization, will geometry be the same as for ground state, or the equilibrium interatomic distances will be different?
They will be different, I believe. Yeah.
Why?
Well, with any I guess energy distribution or any if a molecule has different energies or a different energy distribution, I guess you would expect it to have a different geometry just because of how the charge sort of impacts. How I don't know how to explain. How the charge just interacts within the molecule.
Okay. So you are thinking that one part of the molecule will be more negative, another more positive. They will attract or repel and change configuration.
Yeah.
Okay. If you optimize, if one optimizes it, why the gap, the energy offset between former HOMO and former LUMO changes?
So you're gonna have a lower energy with how do I put this? So the new the excited state is gonna have a higher energy, and then thus I guess it's just gonna have a larger gap.
Or sometimes smaller.
Yeah, or sometimes smaller. Yeah.
So let me give a hint, and you can just approve or disagree. So you create electron and hole, and they experience additional Coulomb interaction. And if they attract each other, the energy will be smaller. Oh, wow, we have another question. So Haley, would you like to verbalize your question to Adam?
How can you calculate the new geometries for the excited state?
The new geometries, you can just, man, I think you can just run another geometry optimization I suppose on the new.
So Adam, do you have example of your in-car for this job?
Example of my in-car?
Just in your slides, can you flip a couple of
Uh-huh.
slides back? Where you show the
I don't think I have like an example for what it looks
you
like.
didn't show the whole in-car, but next slide, forward.
Yeah.
So let me then answer for you, or you can answer cooperatively. What is NSW in when you were doing this run?
I believe it was 10.
What if you tell it to be 1,000?
1,000. You would get further optimization.
Okay, so it is basically optimization of this in-car is in-car for optimization of geometry under constraint for electronic populations.
Right. Yeah. Yeah.
Okay, Haley, does it answer your question?
Yes, thank you.
Okay, yeah, and many thanks for asking it. More questions to Adam? Questions 1, question 2, question 3. Let's thank Adam once again. Adam, you can stop sharing. And I believe the next presenter is Hanmant. Hanmant, would you like to share screen? Okay, let's go to presentation mode, and floor is yours.
Hello everyone. In today's presentation, I'm going to present density of state images for the singlet and how we can do the bond measurement in VMD. So as a first part, I will just show the density of state images for the singlet. So as Umar explained that for preparing the density of states plot, we need to do the geometric optimization, and for that we need to copy the in-car, out-car, K points, and post-car, and the input script file for to the NUSC server. And once we copied that file to the NUSC server, then we will execute the job submission command by using the SBatch, where once we execute the job and once it is get completed, it will create different output files, out of which we can select the outcar file for our for plotting the density of states. So when we are considering these things, so for visualizing this part, we will use the more command to visualize the outcar file. And 1 second. So in the outcar file at 69/17 orbital, we will see the HOMO and LUMO orbits. And plot the density of states, we need to select the sum of the orbitals from the HOMO side and LUMO side. So here I selected these orbitals, and when we are going to input the data for the plotting the density of states using the WASP software, we need some of the inputs for the minimum energy and maximum energy. We can select from this. So once we select this data, that data we will copy to the states file. So we will create the VI states file by using this command, and we will paste that data in that file, and then we will save. And other than this states file, we need some of the data from outcar file. So we will use the grep command for the Fermi energy, for the electron, and for the atoms. And based on that, we will get some of the inputs. So so by using these inputs, then we will execute the execute this command for creation of states file for the energy occupation. So here you can see that these inputs are entered here. So it will finally execute this particular command, and we will get the data for the density of states. So once we will get that data we need to convert into the .ps format. So for that we will use the gunplot software. So we will use this particular command and we will create that particular data into the .ps format. And once we create that data, then we will convert that data into the PDF format. So for that we will use the ps to PDF command, and here we converted that particular data into the PDF format. that data then we will transfer to our local server or Photon server, and from that Photon server to our local computer. So once that particular file get transferred, then we will visualize that file where we can see the electron occupation for the valence and conduction band. So now so this is my first part. In second part, I will show you the how to measure the bonds in VMD. So for that, earlier we did the simulation where we created the movie.xyz file. So first what I will do, I will open the in file, we will click on the file, and then we will upload the molecule as a movie.xyz. And once we upload that molecule, then in the graphical representation, we will select the CPK representation for better visualization. So now once we complete that part, then we will click on the mouse option on the main window, and then we will select the bond as a label. And once we select that label, then we will select the atom which we want to measure the distance. So once we select that atoms, it will show the distances for the particular atom. And once we will run the simulation for all the frames, it will show you the distances which are changing for that particular simulation. So here, as Anand earlier explained that how we create the movies for it, here I created the movies for that, and as per the frame, it will show the different distances for that particular bond. So if you want to see that distances in the data format, so once again we will go to the graphics and we will select the labels, and in the labels we will select the bond. And once we selected the bonds, here for that particular bond we will grab that data where we can see the distances which is varied for that particular simulation as per the frame. Also we can save that data in the that format, and we can use different softwares for plotting it. Thank you. Any questions?
Thank you, Hemant. Any questions are welcome. Let's see if anyone typed any questions. So I see only the previous question of Haley. We should record everything. Okay, I think recording is going on, right? Please check. Yeah, I think it is going on. Okay, floor is yours. Please go ahead, and maybe, yeah, all good.
Okay, so I'm going to be presenting on the computational aspects of light to matter interaction or absorption spectra. So generally speaking, this is all in the field of spectroscopy. Spectroscopy analyzes how light and matter interact. You can look at atomic spectra from this interaction. This includes looking at an absorption spectrum in which you have a electron that absorbs light and then it jumps up to an energy level. Here on the bottom left, we have a little diagram of what this can look like when energy for an electron is absorbed and it goes to a different excited state. On the right, we have what our goal is with VASP when we want to plot these absorption spectra. When we're doing this with VASP, all these calculations I'm demonstrating are done on the NRSC computer, which people have talked about how you log into. I'll be working with a CH or 16 length Loomer CH chain. And prior to calculating the spectra, ideally you've done sort of geometry optimization or some optimization. You get a lot of output files. You at least need the wavecar file. You also want to create a states file based on that has a list of your electron orbitals from your outcar file. This is just a visualization of what the molecule looks like. We need a couple files that we prepared for spectra calculations. First, you create an energy population file. You just name it like so. You can either just directly copy your states file, or if you're just interested in looking at some files around your, or some electron orbitals around your band gap, you can just extract some of them. You then create an input overlap file. I have that pictured on the right here. The first line represents the starting electron the electron number orbital in your energy population file. The second one is the last one. And the third value is just an energy value. And then for future reference, you want to keep track of what your HOMO number is from your energy population or your states file. Then we need to run a few more commands. There are a lot, so there is a advice command you could run to just see what they all are, and then you can copy, paste, and execute them. This first line, I have it numbered, like a description number labeled up at top, and then it's copied with a value down below for what it refers to. The first line is a module swap for libraries. Dr. Colleen mentioned that briefly in a previous presentation. Lines in 2 and 3. There's an executable to make the spectra. Line 4 reads the wave car and it grades the oscillator strength. And line 5 creates only transitions from ground to excited state. One of the output files from all these executed commands is an oscillator strength file. Light is an oscillating electromagnetic field. It's what's kicking it, or it's what's giving energy to these electrons and lifting them up. So if we look into this oscillator strength file, we have different columns. I've labeled 4 of them here. The remaining are labeled on the next slide. This first column is our source orbital. The second one's the target orbital, which you'll get excited to. Third line is the oscillator strength. Fourth line is the energy of our electron. There are a lot of lines that can get produced by this file, and we need to know because each line represents a number of transitions. So you can use the word count command to get that number value. These other files, this slide's been produced by Dr. Colleen. These other lines in the file, one of them represents the number of electrons in your occupied orbital. The next one's your unoccupied orbital. And then we have projections of the transition dipole, which is our electric dipole that represents the transition between energy levels, I think. Once we have all that information, we can finally run a program which will calculate our absorption spectra. You can run this command. You'll get a file that prompts you for different information. Here you'll enter the number of transitions, which you got from that word count value, the min and max energies for these transitions to go at, the electron volt line width, and the HOMO number from your states file. What we get out is a spectrum file. From there, we can just use plotting commands as a GNU program you can plot with. Convert from PS to PDF. You can transfer it to your Photon and then your local computer. When you do that, we get this absorption spectrum plot. I added a couple annotations here. So with an absorption spectrum, you can see like if the visible light range is roughly from 1.6 to 3.26 electron volts. Here, there's a peak around what I think is like around green. So if we were to look at this sample in real life, it would optically appear green. There's also a peak in the ultraviolet. So if you could somehow detect ultraviolet with your instrument, you could expect to see like that showing up. So that's the presentation on absorption spectra. Thank you, and just open for questions.
Please join me in thanking Hadassah. Presentation is open for discussion, and let's see if anyone wants to ask or anyone has typed in any questions. Not yet. From experience from real conferences, typically questions are asked by the next speaker because the next speaker is getting a dose of adrenaline and starts being active and asking questions. Feel free to ask, and I have several questions, maybe even too much. So, practical question. Suppose you are studying a molecular nanostructure, you use this method to compute absorption spectrum, and you compare it with experimental measurements, and you see that your spectrum is different. It shows bigger or smaller band gap. Whom to blame? Or how to improve? What are possible steps to achieve agreement with experiment?
Offhand, I'm not sure. My guess would be to look at the optimization you're doing prior to computing this absorption spectra. You may also look at the let's see, maybe in this spectrum calculation file, there would be min or maximum energy transitions you could modify for your calculation and see what results.
Okay, yeah, thank you for the thoughts. So let me suggest a couple of ideas. So first, this spectrum is based on orbitals from ground state DFT, which are not interacting. So one of the most natural way is to use more upscaled method that includes interaction between electrons and holes in a better way. And we will cover it in the last month of the classes. It will be TD DFT. So it's answer number one. Your advisor, Professor Krzyzewski, would probably suggest to instead of TD-DFT, use beta-salpeter equation or many body perturbation theory. But there are theoretical methods intentionally designed to improve the quality of spectra. So it is the most correct answer. And the fourth man quick fix is just to try different functionals. The calculations that we are doing are for practice are all done with PBE. And later on in the class, I will cover the choice of functional. But if one replaces PBE with one of the hybrid functionals, which are available in VASP, like B3LIP or HSE, the gap may come closer to experiment. Make sense?
Okay.
Just keep it in mind. It could be a practical challenge in your research. Another question. Just we didn't cover it in the class, but try just to share your impression, vision. What is the connection between transition dipole values and oscillator strengths? Are they connected and how?
So I guess my thoughts offhand are the transition dipole connects to the dipole between which levels you're transitioning between. The oscillator strength will, I guess, affect how strong that transition dipole is or how much charge it takes to jump between the two.
Okay,
levels.
yeah, but it's correct, but logic in a different way. So first, one evaluates transition dipole, and oscillator strength is nothing but transition dipole squared.
Okay.
Okay, and do not answer right now, but just make a mark and try to think for the future connection of transition dipole, oscillator strengths, and Einstein coefficients for spontaneous emission. This is something one can find in Wikipedia.
Okay.
If you have an idea, speak now. If not, it's fine. We didn't cover it in the class. Okay, let's check. I see there is something typed. Haley does have the question. Haley, would you like to verbalize your question?
Yeah, how do you change the procedure to reduce an emission spectrum?
Offhand, I'm not familiar with how this code works.
Just general scientific intuition. We didn't cover it in the class. We didn't design the code for emission, but based on your scientific intuition, how to evaluate emission based on the data for absorption.
My guess is you'd see how the energy looks when it de-excites back down, since absorption, electron absorbs photons, and then emission, your electrons de-exciting. So you have a program that would stimulate that like de-excitation or like transitioning down. Be my guess.
Yes. And in your diagram, which is probably for one of for atomic spectroscopy, which of the lines you are showing on the left, you show red, green, blue, and purple. Which line is expected to be the most intense?
Purple one.
No. The lowest one of the available is most intense, because in any system, especially in chemical and solid state systems, the higher state excitations cascade down to lowest available, like to HOMO LUMO, and then from HOMO to LUMO, it is emitted radiatively. So very roughly, the lowest transition in the absorption spectrum will be equal, again, approximately to the emission spectrum. So it absorbs everywhere at each band, at each range of spectra, but emission will happen only from the lowest transition.
Okay.
Haley, does it satisfy your curiosity?
Sure.
Would you like to oppose it and tell that it is incorrect and there are some corrections?
No, that's okay.
But you could tell that this approximation misses from Condon factors. Okay, more questions to Hadassah? Questions 1, questions 2, questions 3. Please join me thanking Hadassah, and the next presentation is by Payman. So Payman, would you like to share your screen? So Payman will tell what to do if the system that one explores for optical properties does have unpaired spin. So practical aspects of optical activity of systems with beyond single. Floor is yours. And I believe we do not hear you. Please check if your
I can hear you technically.
Okay, yes, now you can hear you.
Okay. Hello, everyone. Today I'm going to talk about drawing a spectrum of singlet, doublet, and triplet transitions in a specific system. So let's first define some terms. A singlet state is such a state that all electrons are impaired, which means the spin quantum number for such system is 0. And as you see in this figure, the ground state, we have ground state and excited state, which in both of them, the spin quantum number is 0. We have other systems, doublet states and triplet states. In doublet state, doublet states include the unpaired electrons, and triplet states, all the electrons are in unpaired with similar spin. So based on these definitions, in VASP, first of all, after running the ground state system, we need to do some the modification in in-car file to define the configuration of excited or doublet or triplet system. And also because if we perform any change in our system, the molecular structure change, we can perform the optimization procedure by changing the NSW number in the in-car file. So for example, here you can increase it, and by increasing the NSW, you can get the better optimization. And for applying the different configuration with respect to doublet or triplet, you need to add a command line, n up down. And for example, for triplet system, you can put number 2 for changing the system and to assign the system as a triplet state. Here I analyzed the titanium hydroxide molecule. So first of all, we need to get some instruction. You can use the following command to get the instruction for drawing the spectra of triplet state. And just by applying each step, you can produce files. And based on those files, you can draw the spectra of the specific molecule. So these are the first commands that using them, you can generate the string files. So it's basically at first creates two files, energy pop and energy pop down. We need to create energy pop up based on the energy pop file. After getting these string files, we only need to extract the transitions from occupied orbital to unoccupied. For getting these data, we need to use these following commands using grep command, and these commands will let us to get the only transitions from occupied to unoccupied state. After that, we need to combine these two files, and as you see, the generated file is has a double size of the each of these O string files. After combining all the data in one file, we are able to draw the spectrum similar to the drawing to other figures based on the WC command, and also the second command that you see in this slide. And using the GNO plot, we are able to draw the spectrum. So after that, we get for the singlet state. This is a singlet state of titanium hydroxide molecule. So as you see, all the transition energies occurs after in the region of the visible light. When we apply the triplet configuration to the molecule and doing the same procedure that I explained, we get the spectrum of the triple state that you can see in this slide. And based on this change, based on the changing the transition configuration, you can see that the transition, the absorption shifts to the red region, infrared region of the electromagnetic spectrum, and the absorption reduces in the visible region of the spectrum. So that was my talk. Please let me know if you have any questions.
Okay, please join me in thanking Payman. And presentation is open for discussion. Are there any questions in the audience? Payman presented an important skill to any of us who work with metal organic complexes, iron doped clay minerals, any minerals with doping, and any magnetic materials. But I do have a question slightly different from this transition metals. It is a philosophical question. Try to answer, and even if we fail to answer it right now, it will be related to your project possibly. So it's threefold question. First, consider a material with very small gap. Consider optical absorption, which is motion of electrons from ground to excited state due to oscillating electric field. Okay. So second part will be also statement. Third is a question. Second part, consider connection of this material to bias and inducing it by AC, alternating electric field. There will be electric current with a frequency equal to electric field, and it will be motion of electrons in space. Now, is there any connection between these two processes? Is there connection? Do you see, can you comment on any possible connection between intensity of absorption and conductivity of a material for AC setup?
Yeah, that's a really interesting question. I'm not sure, but I guess because the conductivity is directly related to the gap, I guess. So there should be a relation, because also absorption spectral reveals the information of the electronic structure. So I think there is a direct relation. That's my guess.
Okay, yeah, I'm very happy to hear it and see your train of thought. So yeah, in both cases, the reason for electronic motion is the same, is electric field and transition dipoles between electronic states. So with some factors, one can establish connection between these two observables. Any practical questions to Payman? Questions 1, questions 2, question 3. Please join me thanking Payman once again. So please stop sharing. And we have 2 talks for the remaining 6 minutes if we do not want to go over time. So Amara is the next, and next 2 talks will be maybe the most important for the projects. Amara will tell how to hit the model, and Sarah will tell how to run molecular dynamics. In some communities, it is called NVT and NVE ensembles. So Amara, please start sharing. Floor is yours.
Thank you. Hello everyone. I will talk about the molecular dynamic modeling at or above room temperature. So we use the simulation of any realistic experimental condition involve heat. Geometrically optimized molecule is at equilibrium at like 0 temperature, absolute 0 temperature. So we mostly use the Newshover thermostat for simulation of the system at a certain temperature. And when we simulate the system, a new dynamic variable is added that can accelerate or slow down the particles until the temperature is equal to the desired value. So here, these are the 4 files that we use to submit the simulation, and these are the same files that were used for the previous calculation. There are the 3 steps. First, the geometry optimized model, then the heating the model, and then molecular dynamics. I will explain how we heat the model. So here we use the 4 files: postcard, portcard, K points, and incard. For the molecular dynamic, there is the difference that we use concard file instead of postcard that also contain the momentum. So here the most important step is to modify the incard file for the heating model. The first step is we use this value IBRION 0, because in the molecular dynamic we use its value 0. It determines how often the ions are updated, and for when we use its value 0, it means that the ab initio MD simulation where all the algorithm are destined for the relaxation into the global energy minimum. So it mostly use the valued algorithm for the MD simulation. After that, we use the command SMASS. Mostly in the MD simulation, it controls the velocities and here we use its value -1. It means that we can velocities are scaled back each en bloc step to the temperature. So it helps us to continuously increase or decrease the kinetic energy. After that, en bloc is used, tell us how often the kinetic energy is changed. It is the step after which we reassign the velocities to we reassign the kinetic energy to the original temperature we provided. then the beginning temperature, ending temperature that we want to simulate, and after that IF value that is used to incorporate the ensemble into the system. So here we have used its value to, it's mean that we want to use the NVT ensemble into the system after, but it also used to calculate the stress and force tensor, and it incorporate the degree of freedom. When we use the NVT ensemble, it's mean that we want to use the, we want to allow the change in the positional degree of freedom and kept the volume constant. So after that, NSW and POTIM is the number of steps that are like we need to set these parameters accordingly as we want. After that, we need to submit the job. And what is going on when we when we heat the system, the particle absorb the heat, and it the kinetic energy of the particles increase to a very large scale. It incorporates the degree of freedom to the particle. So as a result, particle can move at position where it can decrease the kinetic energy and increase the potential energy. So when it reaches this point where it has all the potential energy and zero kinetic energy, so we need to avoid this degree of freedom, and we that's why we reassign the kinetic energy again and again to equilibrate the system and get the average kinetic energy. So here these are the commands. We can see our simulation while the job is running, or after that we can, after our job is finished, we can extract the temperature file from the for the plotting. And here in the OGCAR file, you can see that first the temperature was 2500 Kelvin that we provided in the beginning temperature, but after that the temperature decrease suddenly drops to 0, but after 4, when we use the n block value 4, so after 4 it again reassigned to 500, and so after that is the use of n block. After every 4 step, the temperature assigned to the original providing temperature, but it can decrease between these time steps. So here, this is the output of temperature versus time step. Here, I want to mention one thing: the drop in the temperature is the points between the cakes where the kinetic energy is going to decrease due to the potential energy. So after the 4th step, it again reassign into the kinetic energy. So that's all from my side. If you have any question, please.
Okay, please join me in thanking Amara. It's a very helpful practical step that we have, we will do for sure. So let's check. I do not see the questions. Very briefly, at the very beginning, you, in the second slide, you have told that one uses CONTCAR instead of POSCAR. I think you wanted to say that one copies CONTCAR into POSCAR, right?
Yes.
So it just one needs to mention it, because WASP will not read CONTCAR. WASP will look into the directory for the file named POSCAR. Okay, and where the kinetic energy, where the momenta of each ion is stored?
In CONTCAR file.
Okay, good. I'm happy. Let's thank Amara once again. And you can stop sharing. And the last but not least is presentation by Sarah. Sarah, would you like to share a screen?
Sure.
Thank you. Okay, and I have seen slides, so it will be molecular dynamics, which is the next step after heating the model. But the important aspect of Sarah's work that she will give a tour over additional keywords in WASP, which we all need to master as we go through this activity. So floor is yours. We all are listening.
Okay, so basically our simulation should be done after what Amara did. So after copying the count car from heating to a bus car and keep it in a new folder. So you can do many different simulation, standard mecharodynamic simulation or NVE, which is the main topic I will discuss today. Also, you can study the slow growth or maybe metadynamics to study some rare reactions in your system. And also you can use NBT where there is constant pressure on your system. So basically, all the keywords and specific keywords for every task are specified in VASP manual, but today I will only cover the MVE system sample. So basically, you can do NVE or NVT or MBT sample using different thermostats. NVE basically has two methods, so I'm gonna cover today. And NVT for heating or maybe studying also the system can be done using different thermostats. The most famous one is the nose hover one. And also the MBT is available only one thermostat, which is the Langevs. So let's continue. So here I'm gonna study the MVE system. So I'm new to this too, so I read the manual of VASP and they recommended two different methods. And so the first method is the one we covered in the lecture where in the keywords, you need to make sure the MDAL growth should be 0 and SMAS should be -3. And don't set the ISIF, so it will be the default one, which is 0. The other method, they recommend to use the MD algo to be 1 and to use a different thermostat, which is Anderson thermostat, but you will set the collision to be 0. So basically you're using the theory without applying the main part of it. So you keep your NVE applied. So yeah, I will test both of them, but let's go through the other important keywords for the MD simulation. So here, of course, we will set the I-burn to be 0. For the bottom, I use small steps just to make sure everything going slowly, and because I'm studying interaction between molecule and some framework, so it's recommended to have small bottom steps instead of one, of course. So here the number of ionic steps, I set it to 5,000 because the total time of simulation will be the multiplication of 0.4 times 5,000, and I need to run for 2 picoseconds. So that's why I set this number 5,000. My temperature of interest is 300, and this is a picture of my beautiful system. Okay. So this is the overall look of the in-car. This is the electronic steps, which is the usual ones. The MD parameters here, just the additional thing is not to write too much. I don't write charge and wave car. And here is the method related MD simulation, which is MD alog and SMS. And they didn't use the Van der Waals course. And here's the polarization just because I was running on CCAS and it's not that fast. So I needed to set this. Quickly, to submit any VASP job in the VASP and in CCAS, you just need this batch script, and you will only set your job name and number of cars and wall time, number of cores and wall time. And here you can choose either you use and join the standard VASP or JAMA or NCL. So basically, we use standard most of the time. So it's just that simple. Just prepare your file and queue sub your job. I also prepared a quick batch file that collects data from my outputs. So once you run the simulation, you will get a lot of outputs from in these simulations. So this one, just batch submission. This file will collect the data and upload them in beautiful figures. So yeah, so now we submitted the simulation and we made sure from a heating simulation that our system reached the required temperature. So from NVT simulation, the one Amara just described, here I will see, okay, my system almost, the mean temperature is almost as a desired temperature, 300 something, like 310 maximum, and here it's also converged. So now I'm ready. I will take the content car and convert it to VOSCAR in a new folder and submit my NVE simulation. Here I use the first method. Of course, the simulation is not that fast, so you don't have a lot of steps here to compare fairly, but even though the temperature is fairly enough at 300, I know it's fluctuating a little bit, but it's accepted, I guess. I don't know, maybe Dr. Dimitri can confirm that. But this is the mean temperature here. It's almost at 310. And here it's, yeah, it's show you at every step. The temperature and the energy is kind of convergent. The other method, which is using the Anderson thermostats. So here, I don't see that much difference between both of them, and I don't know why they recommended this method. But again, it's not very long time simulation, so it's not quite fair. I would compare again once the simulation is done for like 2 picoseconds to fairly compare the two methods. So yeah, so far it's not that much different between them. So here my system video. And so basically the molecule is going away from the framework. It's kind of expected for EMD to Ab initio EMD simulation to overestimate the distance between molecules and frameworks, but it's not fair. It's not interesting to compare only one framework. It's interesting to compare like at different temperatures and compare different molecules interaction with the molecule, and also to use a numerical data analysis like the mean square displacement, where you see the numbers in a graph and you can compare different temperatures and different molecules in graphs, not the visualization like here. I don't see much. So I tried to do this using a software that I'm mainly using for VASP analysis. It's called VASPKit. It's interesting and very useful, but I tried today to do the MD part here using calculating the mean square displacement, but I found a bug. It's not working, unfortunately, so I don't have data to share with you guys today. But yeah, this is so far what I can give you about NVE simulation on VASP. And yeah, I'm done, and yeah, looking for questions.
Okay, please join me in thanking Sarah. It's an important talk that will add functionality to all of us as researchers. So any questions from the audience, typed or verbal? I do have one quick but important question. So looking forward to mini research projects. So why do we need molecular dynamics? Which observables related to experiment one can extract from such exploration? Like, what would you benefit as a researcher from running molecular dynamics?
For my research, mainly I want to see the diffusion coefficient of different molecules in my system at different temperature and compare them. So standard DFT can only give me the static reaction and zero temperature, while some experiments observing different behavior at different temperatures and different behavior for different molecules at different conditions. So especially diffusion of molecules, or atoms, like in batteries or other systems. So in this system, Ab initio EMD is very useful to explore.
Excellent, excellent. Thank you. Let me complement your answer. So Sarah did mention migration of ions or molecules in space, diffusion. If it is a chemistry problem, molecular dynamics can be helpful to observe motion in space associated with bond breaking and formation. And there is an important aspect that is literally important for Hadassah and Haley. So I will answer right now, but just try to think are the benefits of the molecular dynamics. When ions are moving, the electronic structure is being perturbed at each step of the dynamics. And by exploring molecular dynamics trajectory, one can evaluate the coupling between electronic and nuclear degrees of freedom. So just looking forward into your research projects on a few years, I'm confident that both Hadassah and Haley will do this aspect. Just think ahead. Maybe all of us will do it as well. Okay, last chance to ask questions. Questions 1, questions 2, questions 3. Please join me in thanking Sarah and all speakers and authors of the questions and discussion for today. So from now on, you all are certified experts in computational modeling of material with WASP software. And starting tomorrow, we will focus on the research projects in the lab. So please develop your ideas what to do. During the lab, I will make one-to-one brief, like 5 minutes interview, and we will launch jobs related to your projects if you haven't done so. Okay, meeting is done. Everyone is welcome to disconnect if you haven't disconnected yet, and I'll stay here just in case there are some quick questions.